today, and I have another lecture tomorrow. We're going to try to sort of sketch out a little map over what this thing called anthropic reasoning is. We'll look at some problems and paradoxes, mainly today, and then tomorrow look at some interesting applications of this kind of toolkit. Let's start with just a couple of minutes looking back at where this came from. And this is my sort of personal subjective take on the history. This one day, like a proper historian of science should look into this and then do it in a serious way. But my impression is that the field really got started with some works by the mathematical physicist Brandon Carter in the late 70s or early 80s. Now you can find precursors before that. There are some passages in the writings of David Hume, for example, that kind of foreshadow some of this. And if you squint, you can kind of find premonitions even earlier in Kant and Empedocles, if you really want to try. But Carter was the first, I think, to really put it together and to do something non-trivial and interesting with it. Tomorrow we'll probably look at some of the applications to which he put anthropic reasoning. One of the things that he failed to do, however, was to explain these principles that he was using in clear enough terms to enable others to do what he had done. So I think his applications actually make sense and are very interesting, but his explicit formulations are not so good. And I think that then led to this second phase of anthropic reasoning, which we might call the age of confusion. And I think Carter is partly to blame for that. Then there was a very interesting book that made a big splash and really popularized the field of anthropics, the Anthropic Cosmological Principle by John Barrow and Frank Tipler, which contains a lot of juicy stuff about all kinds of interesting topics. And it was widely read and really stimulated a lot of young minds to think about things they hadn't thought before. But what I think it didn't do was to, again, sort of clarify exactly what the essence of anthropics is. Now, to be fair here, Carter's initial formulations were vague, so there is maybe no objective fact to what you can read into them. You might do different interesting things. To me, the interesting core of anthropics, however, is anthropics as the study of observation selection effect. And we'll talk more about what that is in a moment. But it's quite distinct from this other strand within the rubric of anthropic reasoning, where it has come to mean almost a sort of mystical force that somehow steers life on its path towards some sort of predestined outcome. And it might be that Barrow and Tipler actually were quite clear about this distinction in their own mind, but I think the book, which was widely read, then encouraged a proliferation of anthropic principles. So Carter had two initially, the weak and the strong anthropic principle, and even there the distinction was not very clear. Barrow and Tipler introduced another two, and then after that the barn door was open, and I counted more than 30 back in the late 90s when I lost count of this. And it's kind of come to mean anything and everything at that stage. And one unfortunate consequence of that was that anthropic reasoning kind of fell into disrepute, because a lot of serious people were encountering this maybe for the first time in one of these sort of derivative and distorted principles and thought, this does not make sense. Why should we have to assume that there is a mysterious force that guides life to its predetermined destiny? That just seems bogus. And so there were this tension between some people who felt, particularly some cosmologists who were like actually finding this useful and needing to resort to this kind of reasoning to get their work done. And then on the other hand, people in philosophy of science who looked at this and said, this doesn't really make sense. But I think that's because there were two different things going on under the same name. The next significant contributor to the foundations of anthropics that I would mention in this short history would be John Leslie, who is a philosopher. And he clarified a lot of these kind of misunderstandings. And he also brought to the fore the Doomsday argument, which we'll encounter again later as a particularly kind of interesting application. He also wrote about the applications of anthropics to cosmology. The Doomsday argument had actually, Leslie tells us that he first heard of the idea from Brandon Carter, but Carter never wrote it up. There have been many others, but I'm not going to go into all the names and people who have made useful and important contributions here. But still today, I think there are kind of two different lives that the anthropic principle leads. One is in physics, particularly in cosmology, and we'll hear a lot about that in this conference. To some extent, it also pops up in foundations of quantum physics, maybe in the foundations of thermodynamics, thinking about times arrow and stuff like that, there are applications. And then a relatively distinct strand within philosophy, where a little cottage industry has sprung up over the past 15 years or so, focused on the Sleeping Beauty problem, which we might mention later. And unfortunately, these have been relatively isolated from one another, which I think is a pity, because sometimes what you see is the discovery within one of these subsets of practitioners of some proposed solution that seems to solve all the problems in their domain. But then when you try to apply it in cosmology, or if you try to apply the cosmologist principle in the philosophical thought experiments, you immediately see that it breaks down. So I think what would be really useful for the field to progress would be more communication between the philosophers and the physicists. But I'll try to cover some examples from both areas and see if we can encourage that. So much for history. Now let's dive in. To me, the best place to start to kind of sketch out what anthropics is all about is in terms of this assumption, which I call the self-sampling assumption. This focuses in on anthropic reasoning as taking into account observation selection effects. And I believe that this was what Brandon Carter had in mind, more or less. The self-sampling assumption says that one should reason as if one were a random sample from the set of all observers in one's reference class. Now, there are a couple of terms here that would require more work if one wanted to make this precise. The term observer and reference class. Well, if you had a very crisp definition of reference class, you might omit the term observer. You might just say random sample from the set of all objects in one's reference class, and then sort of the definition of the reference class could do all the work. There are some strengthenings of this principle that will be useful, particularly in applications where you have the dimension of time as an important variable. You might want to use the strong self-sampling assumption, which would say exactly the same thing, except instead of talking about observers, it would be talking about time segments of observers or observer moments. So the strong self-sampling assumption would say each observer moment should reason as if it were a randomly selected sample of all observer moments in its reference class. And for some applications, it's necessary to move to this stronger self-sampling assumption. The spirit is very much the same. And we'll stick with this simpler formulation, except if the other one turns out to be needful in a particular application. So there are some arguments for accepting this. One derives from various thought experiments one can conceive. So imagine that we have a world that's otherwise empty, but it has these 100 rooms, and God begins by flipping a coin toss. Now, in the setup, we must imagine God not to be an observer in order not to confuse it. You could imagine a mechanical machine doing this instead, not to complicate things. So a mechanical machine flips a coin, and in these 100 rooms, it either incubates one person, or it incubates one person in each room. So we have a world of either one observer or 100 observers. Actually, let's start really simple. Let's just suppose that it just incubates 100 observers no matter how the coin fell. This is the simplest case. We have a world, 100 observers, each in a room, but I can't see which room they're in because it's dark in the room. And now you're one of these observers. You have just been born into this world, and you can be asked about what probability you assign to different hypotheses about which room you're in. Maybe on the outside, each room has a number pasted on it that you can't see from the inside, but you can ask yourself, like, what's the chance that this is number 1? What's the chance that it's number 2? What's the chance that it's in the range of 10 to 100? And it seems intuitive to start with that in this position of ignorance, you should distribute your credence evenly between these possibilities, either one of which, for aught you know, could be the correct one, and they seem equally simple. one can fortify this reasoning by considering that if you accept this self-sampling assumption in this case and you are asked to bet money accordingly, then the universal acceptance of this principle would lead, for example, to most observers thinking it's very unlikely that they are in room number 1. It's like a 1% chance. And if they bet accordingly, that they're probably in one of rooms 2 to 100 rather than in room number 1, then 99% of them will win their bets. If they have some other kind of principle of betting, where it concentrates the probability on some arbitrary subset of these, then as a group, these observers will tend to lose money. One can also consider limiting cases here. So suppose that we modify the experiment slightly, so you have these 100 rooms still with observers, 1 in each room. Now the rooms are painted either blue or red on the outside. Again, you can't see it from the inside. We can start with a case where half of the rooms are painted blue or red. It seems plausible to assign that a 50% chance then that you are in one of the blue rooms. 50% of the rooms are blue. But then you can consider a sequence of cases where the fraction of rooms that are painted blue increases. The self-sampling assumption says that your probability goes up according to the increase in fraction of rooms that are red. So that when you reach the limiting case where all the rooms are red, you should assign probability 1 to you being in a red room. And in this limiting case, of course, you don't need to invoke the self-sampling assumption. You can just use logic to deduce it. If you know that all the rooms are red and I'm in a room, then you can infer that the room I'm in is red. So the self-sampling assumption nicely converges to this extreme case, which everybody should agree to. And it seems unreasonable that there should be some radical jump when you paint the last room red. It seems much more plausible that the credence should kind of follow reality in this way. So another type of argument for the self-sampling assumption is by looking at how it can do useful work in various areas of application, particularly in cosmology, where it seems necessary to use something like the self-sampling assumption. And I will leave it open whether the self-sampling assumption is exactly correct in its current form. This is like a first stab of something roughly in this direction seems perhaps to be needed. But these arguments might not pinpoint this particular formulation as the exactly right one. But in cosmology, it seems something like this is needed to be able to derive observational consequences at all. And it has some other useful applications. So let's zoom in on this and look at this a little bit more closely. So suppose you have a theory that says that there are 100 universes. 90 of them are type A universes containing no life. 9 are type B universes, so they each contain 1 million observers. And there's one type C universe, which contains 1 billion observers. Now, again, if we instead had a theory that didn't postulate this type C universe, so it just had the first 2 types of theories, then we wouldn't need any sophisticated anthropic principle. We could just use logic after you have discovered. Now, if you ask what the theory predicts that you should observe, you would get the answer that it predicts you should observe a type B universe, since the type A universes can't be observed. But once you introduce this third possibility, it becomes a little bit less trivial, because here you have to start to take into account the numbers of observers. It's certainly logically consistent with this theory that you might observe either a B or a C universe. So how can you derive any observational consequence from this type of theory? And here the self-sampling assumption is one principle that would help you do that. It should say, with overwhelming probability, you should expect to find yourself in a type C universe. A randomly selected observer among these 1 billion and 9 million observers would be in type C universe. So you can kind of find a way to connect theories that postulate some distribution of observers, or more generally some objective description of the world, with some hypothesis about what you should expect to see if that theory were true. That is, it connects hypothesis about which possible world you are in with hypothesis about which centered possible world has you its locus, to use philosopher's terminology, or in yet other terminology, indexical facts about who you are, what time it is, where you are. Via the self-sampling assumption, information about indexical facts can be brought to bear on non-indexical theories. We can also consider even more starkly the situation in a big world cosmologies, which we'll probably hear more of over the coming 2 days. So a big world is one, in my terminology, which is large and varied enough that it contains at least one instantiation of all possible observations that a human could make. So imagine sort of human brains in all possible states. And it looks that many current cosmological theories imply that the world is big in this sense. Like if it's infinite, then it's almost certainly big, just because you have a lot of random places where things can happen with some trivial probability, but still some non-zero probability. And if you just repeat these kind of random independent processes enough times, you'd find all possible combinations. So then the question arises, if you have a cosmology that implies a big world, then how could you derive anything at all in terms of what we should observe from it? Because it seems that whatever observation you make, the theory is logically consistent with it. It says somebody should make that observation. And yet, it appears that cosmologists are testing these kind of theories all the time by figuring out what they imply and then seeing if that fits our observations. And here again, the self-sampling assumption comes in and provides a bridge that enables you to test these things. So although in big worlds all possible observations are made, yet different big world theories would imply that different types of observation are made with different frequencies. So to make this work in the infinite case, you would need to generalize it from just counting the number of observations of each type to something else, like a limiting frequency or the density of observations. And exactly how to do that in the general case is an open question. But it seems clear that some generalization of that kind would be necessary and that it might then hold promise to create this bridge. So those are some arguments for accepting it, and its usefulness in other domains we'll get back to when we actually look at some applications later today or tomorrow. Now, it also has problems, unfortunately. So one of these is the Doomsday argument. Now, whether the Doomsday argument is a problem in the sense of being an objection to the SSA or not is maybe slightly controversial, but certainly the other two that I will talk about shortly are very counterintuitive and must count as objections. So the Doomsday argument, I don't know how many of you have already heard about that. I'd imagine quite a few, maybe half. Well, so in a nutshell, it goes like this. Well, it's easier to explain via a little metaphor first. So suppose that you have an urn with balls in it, and the urn was filled either with 10 balls or with 1 million balls, depending on the outcome of a random coin toss. And then this urn is put in front of you, and your task is to guess whether it has 10 balls or 1 million balls. So you say, well, it's 50-50. I mean, I haven't seen how the coin fell. It's a fair coin. It's clearly 50-50. So far, no problems. Now, let's imagine that these balls are numbered from 1, 2, 3, up to either 10 or 1 million. And that you're allowed to pick one random sample from this urn. So you put in your hand, you don't feel around too much, so you can't feel how many there are, but you pull out one ball and it's number 7. So this gives you very strong evidence that there are only 10 balls in the urn. The probability of picking out number 7 is vastly greater if there are only 10 balls, it's like 1 in 10, than if there are 1 million balls, then it will be 1 in 1 million. So by just doing a standard Bayesian update, you then get a posterior probability that overwhelmingly favors the hypothesis that the urn has 10 balls. So this is not controversial at all, but the Doomsday argument says that you should apply a similar reasoning where instead of having 2 different urns with different numbers of balls in it, you have 2 different hypotheses about how many humans there will have been when human history one day ends, when humanity goes extinct. So you could have one hypothesis that says that in total there will have been, say, 200 trillion humans, and then some disaster occurs and we go extinct. And another hypothesis that say that there will be, say, 200 trillion humans when our world ends. So those correspond to the different hypotheses about how many balls there are in the urn. Then this random sample that you picked out, ball number 7, when we translate it into the Doomsday argument, it corresponds to you discovering something about your own birth rank, that is your position in the sequence of all humans that have ever existed. So there have been a finite number of people before us, and maybe around 100 billion or 200 billion. So you find that you have a certain number that is consistent with both of these hypotheses that you are considering. But there are many more observers on one and fewer on the other, but both of them agree that there would be at least this number of observers. And by exactly parallel reasoning to this Earn case, if you crank the wheels and do the Bayesian inference, you then get an update in favor of the doom soon hypothesis, the hypothesis that says that there will be relatively fewer people in total. So this is kind of obviously undesirable for kind of normative. Well, it's like we don't like this to be true. It's not clear that it's an objection to the self-sampling assumption. It certainly would be shocking. What might be an objection is that you could get such a striking conclusion from such meager premises. It seems prima facie surprising and maybe implausible that you could get this strong prediction about when the world will end in the future, when nuclear war will do us in, or doomsday weapons made by synthetic biology or whatever, from just doing some little simple kind of thought experiment in your head. So to the extent that that's counterintuitive, this is an objection. Let's see, before I proceed, let me just fill in a little more, since the doomsday argument has kind of interest in its own right. So you might wonder, surely there must be other things that affect the risk of extinction. Like if we bring peace to the world and collaboration, and we have all these wise people who are constantly looking for existential risks, then surely that should decrease the probability that we'll go under soon. Conversely, if we begin to build very dangerous new weapons, or if we see like a meteor hurtling towards the Earth of vast size that we can't divert, surely that should make the probability go up. So any argument that wasn't sensitive to these things must be wrong. And that's true. But again, the doomsday argument can accommodate this. In its more sophisticated version, what you're supposed to do is first assign a prior empirical probability based on all these normal considerations, your best guesses about different particular danger scenarios. And then you make this probability shift on top of that. The thinking being that although maybe you knew all along what your birth rank was, so it's not new information, yet you did not realize until you heard the doomsday argument that this information that you had all along was actually relevant in this way. So it's kind of all the information that you have failed to fully take into account is the idea. But the ordinary empirical information is still there and will affect the outcome. But you'll still get a fairly, for sort of realistic values, you still get a fairly strong shift in favor of doom soon hypotheses. Now, these other thought experiments here, the Adam and Eve thought experiment and the UN++, follow the same form. In spirit, they are sort of similar to the doomsday argument, but they bring out the counterintuitiveness in this more stark way. The Adam and Eve thought experiment goes like this. So let's imagine that there was once the first two humans, like Adam and Eve, fully formed, inhabiting the Garden of Eden. And now they are in a very strange position because either if they've gone to embrace one another in sin, they might give birth to a whole species that will then fill the earth with misery, and there will be billions and billions of people. But they'll then be in this very unusual position. They will have been the first two, like out of billions. It's a striking thing to think. Or they might do this carnal embrace thing, and maybe she will not get pregnant, and then they'll just be the first two out of two. So their position will be very typical. Well, you can see now that if you apply the self-sampling assumption here, they can be overwhelmingly confident that even if they do indulge their fleshly desires, that she will not get pregnant. Maybe sort of the biological prior is 1/2 or 1 in 10 or something. But once you down modulate that by this factor of 1 billion or so, the chance becomes trivial. And it seems counterintuitive that it would actually be rational for them to reason in this way and then go ahead and take this risk. You could imagine an adaptation as well. They wake up one morning, they're like lying in their cave and they're kind of hungry, but Adam doesn't feel like going out hunting. He's lazy. So they could instead then maybe form the firm intention that unless a wounded deer just happens to limp by the cave within the next 10 minutes, then they will go on to procreate and fill the earth with billions of progeny. So now they know that either they will be among the first 2 out of 2 and the wounded deer will limp by the cave, or if no wounded deer limps by the cave, there will be billions and billions of people. You evaluate the probability of these 2 different hypotheses, and assuming you sort of make the numbers large enough, the improbability of being the first 2 among billions will overwhelm the improbability of a wounded deer conveniently limping by. And it seems very strange to think that you could actually use this to hunt. And the UN++ is essentially the same, except it says that we might sort of actually be in the situation of Adam and Eve if, with some hand waving, if we had the capability of forming firm intention as to whether we should colonize the universe or not. So it's not only in these kind of counterfactual thought experiments, but situations could conceivably arise where we could, if this kind of reasoning were correct, where we could utilize it to apparently bring about these sort of causally anomalous effects. Now, I argue that there wouldn't actually be any sort of, if one properly analyzes this, it wouldn't properly involve anything that should be interpreted as paranormal causation, but still it's an extremely strange implication. So those are some of the problems there for the self-sampling assumption. Now, one way to overcome these problems is by introducing this other assumption, the self-indication assumption. And it says that given the fact that you exist, you should, other things equal, favor hypotheses according to which many observers exist over hypotheses according to which few observers exist. So the thought could be that the fact that you exist in the first place gives you some evidence that this world is sort of an observer-rich place. And you can see how, if it did accept this, it would remove the counterintuitive consequences of the self-sampling assumption. So take Adam and Eve again. They wake up, maybe initially they haven't figured out where they are. They just exist in a cave, but they don't yet know whether they are Adam and Eve, the first 2 people, or whether they are just sort of campers who got too drunk the night before. But in this situation, before they know that they are among the first 2, they would, if they accepted the self-indication assumption, assign a much greater probability to the world being one that had been filled by billions and billions of people. In fact, in proportion to as the number is larger, the self-indication assumption says that the hypothesis should gain sort of a prior credence. That doesn't mean you shouldn't also take other considerations into account. The simplicity of the world and such like that would also be consistent with the self-indication assumption that you should assign probabilities based on that as well. But other things equal. 2 equally simple world, if one has 10 times more observers, should have 10 times the prior probability, according to the self-indication assumption. So Adam and Eve wakes up, they think, it must be a big world because, hey, we exist. So at that point, they are overwhelmingly confident that the world is big, and that if there ever were a scene once upon a time when the first 2 people made this resolution to procreate unless a wounded deer limped by, they have a very strong guess about how that went. It must have went in such a way that no wounded deer limped by, they procreated and filled the earth. That way there would be more observers. Then, when they discover that they are actually among the first 2, you get this doomsday argument-like probability shift in favor of fewer observers, because that would make their position more typical. And that shift exactly counterbalances this prior shift in favor of more observers. So the doomsday argument and this initial bias towards more observers cancel out. And you avoid these counterintuitive effects. And that's really neat and elegant. So even if initially it seems, why on earth should you think that the world is more likely to contain more observers just because I'm born? It seems kind of an arbitrary idea. There are arguments for it, particularly that it resolves these paradoxes. Also, that it eliminates the dependent on the reference class. So here we have this kind of unspecified parameter, like which entities should be in your reference class. But it turns out that with the self-indication assumption, it doesn't matter how you define the reference class. So that's some arguments for it. Let's illustrate this in a little bit more detail. So here we have a simple thought experiment where you have, instead of the 100 rooms before, you have 2 rooms now. Okay, the same coin toss determines that either this is the whole world, there's one room with a guy with black beard, or if the coin falls heads, then you have 2 rooms, guy with black beard and a guy with white beard. They start out in darkness, so they don't know what color beard they have. They just pops up in this room. Now, we use the self-sampling assumption first. Let's ignore the self-indication assumption for the moment. You ask, what's the probability of heads? This is before you have any other information, before the light has come on. You don't yet know what color your beard is. And you say 1/2 because, hey, it's a fair coin. That's all you know. Then you can also consider what is the probability of the coin having landed heads, given that you have black beard. And here we get 1 in 3. This is basically the Doomsday argument shift. If heads, then it's like 1 out of 2 observers has black beards, whereas here 1 out of 1. So the conditional probability of having black beards is larger in this world than in this world. And so you get this shift in favor of fewer observers. Since here are more observers, this goes down below 1/2. Now, if we use the self-indication assumption, then when you first wake up, you don't yet know what color beard you have. You have not 1/2 now for heads. You have one, that should probably be 2/3. Yeah, should be 2/3 there, because there are more observers there, twice as many in fact, as in the first case. And here is a counterintuitiveness itself. Like, you know the coin is fair, and you haven't looked at it, and just by thinking about this, you should now assign some different probability than 1/2 to the coin having fallen heads, namely 2/3 in this case. Okay, but then when you discover that you have black beard, or if you just sort of think about the conditional probability in advance, you then get back the prior probability, and you can sort of, if you're familiar with Bayes' theorem, you can just work out the numbers and see that that works. But now consider this slightly different modification where instead of having an observer in room 2, you have a rock. Something that is not intended to be in the reference class. So here the self-sampling assumption suggests that after discovering that you have a black beard, the probability of heads should remain 1/2, because all the entities in your reference class are black-bearded men, whether or not the coin fell tails or heads in this situation. So you don't get any shift there with the self-sampling assumption, which means that the probability remains 1 in 2, which is different from what it was here, right? So here we got 1 in 3 as the posterior probability after discovering you have black beards, and here it's 1/2. So the probability has changed. So depending on what you put in the second room, whether that counts as being in your reference class or not, you get a different answer with the self-sampling assumption. On the other hand, the self-indication assumption, its answer doesn't change. If you think about it, whether or not you count this as an observer or not, the self-indication assumption still gives you the answer 1/2. So if it's not an observer, then there are the same number of observers in either case, therefore the prior doesn't change, and you don't get this SSA shift. So that's a neat feature about the self-indication assumption, that you remove this dependence on the reference class. So these are strong arguments in favor of the self-indication assumption. Unfortunately, there is also a problem for it, which is, I think, the thought experiment that I will end on today, and then we'll pick up tomorrow where we left off today. So the presumptuous philosopher thought experiment, it goes like this. Imagine 100 years from now that physicists have narrowed down the range of possibilities into two remaining candidates, two remaining cosmologies. And they want to assign these two theories about equal probability because they're equally simple, they equally well fit like all the ordinary evidence and so forth. And they differ only in this way that according to one of these theories, there are a trillion observers in the entirety of physical existence. And according to the other theory, there are a trillion observers. It's a bigger universe, but otherwise identical. Now, the self-indication assumption suggests that you as a philosopher aware of this self-indication assumption can be overwhelmingly confident that the first of these two theories is correct. In fact, it's a trillion times more likely. And that seems unjustified. Maybe there is some simple experiment that the physicists want to conduct in order to finally resolve this one remaining uncertainty. And maybe it will cost $100,000 merely. It's like a simple little thing you need to attach to a satellite, and it will find the needed data. But the philosopher comes in and says, oh, there's no need to bother. I already know with much greater probability than you could ever find out that it's theory A that's true because theory B that's true, the one with a trillion times more observer. That's a trillion times more likely, and it's just not worth carrying out the experiment. And you could elaborate on this more. You could imagine maybe instead of one crucial experiment that tells the difference, there's like a series of experiments, each of which brings in new strong evidence in favor of theory A, the smaller number of observer theory. And each time, even though the philosopher keeps losing, he mortgages his house, he goes around asking all his relatives and lose their money too, and yet his confidence remains unshaken. And that's counterintuitive, and one reason maybe to be dissatisfied with accepting the self-indication assumption. But it seems that either way you turn, it's difficult to escape accepting at least something very counterintuitive in this domain of anthropic reasoning. Thanks.